In this video, we are going to work through an example of solving an initial value problem that involves a non-homogeneous differential equation using the variation of parameters method, right? So we kind of look at it, everything seems to be in order. There's our nullity, there are our initial conditions. And since it's non-homogeneous, we're still going to use that superposition principle that requires us to find the complementary function as well as a particular function. But again, we're going to use the variation of parameters because our function on the right here isn't one of our nice standard ones. In fact, this is a function that involves taking an exponential function and dividing it by a polynomial. And it's that division that really makes this problem tricky. Now, in the variation of parameters method, it is important that we have a leading coefficient of 1 as our in our differential equation. So in other words, the first thing I'm going to do before I start solving anything is just go ahead and I'm going to divide the entire both sides of the equation by 2. So that will get rid of this 2, this 2, this 2, and it will make the middle coefficient on the left a negative 2. So if I divide by 2, then this is our dE. And that's one of the first things that you'd want to do. Now, you don't necessarily have to do it right at the start, but certainly before you identify the f of x that's needed in the variation of parameters method, you want to make sure that that leading coefficient is 1. So there we go, right? It's the same dE, just dividing both sides by that what was our leading coefficient. So now let's go through and start finding the pieces of our general solution. So for the complementary function, I need to solve the corresponding homogeneous equation. So that's y double prime minus 2y prime plus y is equal to 0. So let's write down the auxiliary or characteristic equation. So m squared minus 2m plus 1 is equal to 0. We can see that this is a perfect square. This is the quantity m minus 1 squared equals 0. So we're actually going to end up with a repeated real root. So this is case 2. So our m1 and our m2 are exactly the same. And what do we know about that? We know that our fundamental set or basis consists of these two functions. So y1 will be e to the 1x, and then y2 will be x e to the x. And again, that's because of that reduction of order process, right? So, if you wanted to write your basis like this, you could. And it's important to make note of these functions because you need these functions when we apply the variation of parameters method, right? In addition to writing down the basis, I'm going to write down our y sub c, which is the general solution of the homogeneous equation. So it's c1 e to the x plus c2 x e to the x. All right, so there we go. We can't really say we're 50% complete, but we have at least one part of the general solution. Now, for y sub p, again, you don't have to write it down, but I like to show where these things are coming from. I'm going to write down the system that allows us to solve for u1 prime and u2 prime. So it's u1 prime times y1 plus u2 prime times y2, and that's equal to 0, right? And then the second equation is u1 prime times y1 prime, but the derivative of e to the x is still e to the x, and then plus u2 prime. Now I have to find the derivative of x e to the x, so I have to use the product rule. So that is e to the x plus x e to the x, and then that is equal to now my f of x. Well, what's f of x? f of x is the function on the right-hand side when my differential equation is written with a leading coefficient of 1. So my f of x is this, e to the x over x squared plus 1. So it goes there, right? So that's where that function on the right comes into play. All right, next up, let's write down the determinants that are needed when using Cramer's rule to solve this system for u1 prime and u2 prime. So let's write down the three determinants. The first one is our Wronskian, right? In fact, we have the e to the x, and then x, e to the x, and then e to the x, and then e to the x plus x e to the x, right? So let's go ahead and compute it. So we have to take e to the x and multiply e to the x plus x e to the x, and then minus x e to the x times e to the x. So if we distribute this, what do we end up with? E, we add those exponents, so we get 2x, and then we'll have x e to the 2x again, so x e to the 2x. But then over here we have minus x e to the 2x. So that's nice. The Wronskian comes out to be e to the 2x, which we know is never 0, right? So none of our previously developed theory is broken, or Wronskian is never going to be equal to 0, because the elements of my fundamental set must be linearly independent, all right? Then let's write down the other two determinants that we need, starting with W1. And that's where we replace the first column of W with the functions on the right-hand side. So the expressions on the right-hand side. So the 0, and then the e to the x over x squared plus 1. And then the second column stays the same. So I have x e to the x, and then down here, what do I have? I have e to the x plus x e to the x. Now again, using our AD minus BC, the product of those functions on that main diagonal is 0, and then minus, when I multiply these two, now think of this as being over 1, so I'm multiplying those numerators, I'm going to get x e to the 2x over x squared plus 1. So then that simplifies to negative x e to the 2x over x squared plus 1. All right. So that's our W1. And then W2, something similar, where we replace now the second column. So the first column stays as e to the x, e to the x. Second column now is 0, e to the x over x squared plus 1. When we multiply these two, I will have e to the 2x over x squared plus 1 minus, when I multiply these two, I'll get 0. So we have e to the 2x over x squared plus 1. All right. So now let's write down what the derivative of u1 is and what the derivative of u2 is, right? So u1 prime is going to be w1 divided by w. W1 is that negative x e to the 2x over x squared plus 1, and then this is also divided by, so when I'm dividing by w, which is our e to the 2x, I can put that in this denominator as well. And what happens is now the exponentials cancel out. So I have negative x over x squared plus 1. All right. And then let's write down what u2 is, or u2 prime. That's equal to w2 over w. So it's this divided by e to the 2x. So it's e to the 2x over x squared plus 1, again divided by e to the 2x. So that's 1 over x squared plus 1. So now we have to integrate these two. So u1 is equal to, and what I will do for these now, I'll stop writing the constant of integrations, right? The constants of integration. So I'm just going to write down what essentially the base antiderivative is for this function. Now the way this one can be evaluated is by a substitution. Right? Now I'm not going to use u, I'm going to use a different letter. Let me use t for this. So if I let t be equal to the denominator, the x squared plus 1, then dt is equal to 2x dx. I don't have a negative there. Well, I don't have a negative here, and I don't have a 2 here, but I can fix that. What I can do is I can multiply this by negative 1/2 and get this. So negative 1/2 dt is negative x dx. So I can replace this differential by negative 1/2 dt. And then I can, obviously the denominator here is my t. So what does it look like with that substitution? So I'll take out the negative 1/2, and then I have the integral of basically just 1 over t dt. So that's our natural log. So I'll write this as negative 1/2, the natural log of t. Again, I won't worry about the plus c, and then here. Now you might wonder, why didn't I write the absolute value? Well, because x squared plus 1 is always greater than or equal to 1. So it's never negative, right? So I don't need the absolute values there. So my u1 is the function negative 1/2 ln of x squared plus 1. All right. Let's see what u2 is. So u2 will be the antiderivative of 1 over x squared plus 1 dx. But that's our, I said x and wrote t. So dx. Well, this is our arctangent. This is our standard inverse tangent antiderivative. So if you want to write it like that, you can, or if you want to write it as this, you can, depending on what notation you're using for the inverse. But do not, if you're using the negative 1 exponent here, in the context of trigonometric functions, this is not the reciprocal. So let me just put a little note right here. This is not equal to tangent to the negative 1, right? Arctangent is different. It's just kind of it's an unfortunate use of the notation. But in the context of inverse trig functions, this negative 1 is not equivalent to a reciprocal negative 1, right? So this is a reciprocal, this is an inverse, not necessarily the same for functions, right? Okay, so we have our u1 and u2, so therefore, our particular function is, now, so it's u1, so it's negative 1/2 natural log of x squared plus 1 times y1. y1 was our e to the x. And then plus u2, which is our arctangent, times y2, which was our x e to the x. All right. So the general solution. So the general solution is, let me write it down here. Now the reason why I'm going to give myself a lot of room is because since we have initial conditions, we're going to have to differentiate what I'm about to write down. So it's c1 e to the x plus c2 x e to the x minus 1/2, and I'll put the e in front of the ln. I just like having the e there in front. and then plus, and then I'll do the x, and then the e to the x, and then the arctangent of x. Right? Now, just as a reminder, these are the initial conditions. Y of 0 is 1. Y prime of 0 is 2. So we could, I think, looking at this, yeah, so if we can get the value of C1 quite easily. That's easy because notice all the other factors, when I plug x equals 0 in, there will be a factor of 0 because this will be 0. The natural log of 1 is 0, and then again this will be 0. So that one's easy to work with, but it's the derivative that's going to be tricky because we have to differentiate this. So I'm going to write down y prime, and I'm just going to go through term by term, differentiating. So the derivative of the first term is straightforward. The derivative of the second term requires the product rule. So that will give me e to the x plus x e to the x. In fact, that's what we had earlier in our Wronskian. That was that term. We're going to need the product rule here. Now, this negative is going to have to be distributed to both of the terms. So I'm going to take out in fact, what I will do is take out the negative 1/2, since that's a constant multiple, and then just focus on differentiating the product e to the x times the natural log of x squared plus 1. So the derivative of the first, I'll get e to the x, and then I'll have the natural log of x squared plus 1, and then plus the first. Now, to differentiate this, I need the chain rule. So I'm going to have, I'll have 1 over x squared plus 1, and then times the derivative of the inner, which is 2x. In fact, let me just put the 2x in the numerator here. So that's because of the chain rule, right? So now we have this one. And this one is a product of 3 functions. Now, I don't know, like, I don't know if you've seen this before, but there is a nice extension of the product rule. I'll write it down here. If you have the derivative of, let's say, f times g times h. So let's say your product involves 3 factors, and there's no nice way to simplify them. Here's an extension of the product rule for 2 functions. It's you take f prime times g times h plus f times g prime times h, and then plus f times g times h prime. And it's simply a matter of applying the basic product rule twice, right? The way you would do it is you would group the product there like this, and then repeatedly apply the product rule, and you end up with this particular result. The pattern is pretty cool because you notice what it is. Each term here has 3 factors, of the 3 functions, but one of them, in each term, you're differentiating one of the functions. So let me use this result to come up with the last set of terms. There are 3 more terms that we have to write down. So if I start by differentiating the x, it becomes 1. So then I'll have 1 times e to the x times arctangent, and then plus, and then keep the x and differentiate the e. But when I differentiate the e, I'll get back the e, and then I also have to keep the arctangent there, and then finally keep the x, keep the e to the x, and take the derivative of arctangent. So x e to the x times 1 over 1 plus x squared. Yowza. And there you go. All right, so let's see what happens now, because our goal is to find C1 and C2. So when x is equal to 0, y is equal to 1. So I'm going to plug 1 there for y. This will give me C1. This is 0. The natural log of 1 is 0, and then again this product here is 0. So that one works out really easy, as I said earlier, that C1 is equal to 1. Let's see what happens when we plug 0 into this mess of a derivative here. So when x is equal to 0, y prime is equal to 2. So I'll have a 2 there. And now I know that C1 is 1, so I'm going to use that fact. So I'll have a 1 there. Here, this factor is 0 because x is 0. E to the 0 is 1. So there I have plus C2. So I have that. And let's see what happens to all the other stuff. So I'm going to have the minus 1/2. And let's see what I have in parentheses. Again, the natural log of 1 is 0, so this is 0. And then, again, x is 0, so this whole thing is 0. So we have nothing really there, right? That's going to affect the answer, that is. The arctangent of 0 is also 0, right? So we have 0 there. This x is 0, so we have another 0 there. And then here we have another factor of x. So we have all these things. We have all these terms, right, that we had to compute, getting all fancy with our product rule. But when we evaluate them at x equals 0, they're all 0. So what does this mean? It means that C2 is also equal to 1. Just subtract 1 from both sides. So C2 is equal to 1. So therefore, the particular solution, right? So the particular solution is, and it's y equals e to the x plus x e to the x minus 1/2 e to the x natural log of x squared plus 1 plus x e to the x times the arctangent of x. Wow. Again, when you think about what our y sub p is, which is this, there's no way we could have, no matter how educated we are, I don't think we would have guessed this as our y sub p, right? But with the variation of parameters method, there is no guessing. It's just a lot of systematic work involving some linear algebra and some integration techniques, usually the ones that you'd have encountered in your calculus course. So there you go, another example. Hopefully that helps, and we'll keep on pushing along, and I'll see you in the next video.